Welcome back to our series on multivariable calculus. In this episode, we're going to talk about how to find the surface area of one of these 3D functions we've been looking at. Now, surface area is a little bit tricky. We've been looking at density and center of mass, but surface area involves a whole different kind of integral. So let's take a look at it theoretically. Let's begin with a function we're familiar with. I'm not actually going to write out the formula for the function because that's kind of irrelevant. This can just represent any general 3D function we're interested in. Well, what we want to do in order to find the surface area of this is to select a point on it and then to identify the tangent plane at that point. Now, what value does the tangent plane have at that point? Well, the tangent plane brushes by the surface, and depending on how curvy the surface is, it can represent a pretty good indication of the surface area very, very near that point on the surface. It would get to be a better approximation as I made the tangent plane smaller and smaller and smaller and smaller. At the ultimate limit, it would basically be the same size as the tangent point, which means it would, in essence, paper the surface. And then if I could integrate that over the entire surface, I'd have a really good idea of what the surface area was. Well, it turns out we have the mechanisms to do that. Recall that we actually located the plane tangent to a point on the surface. We actually located that by taking the cross product of two vectors found from partial derivatives. If you'll recall, they look like this. The first one was 1, 0, fx. And that was basically a vector that pointed along one edge of that tangent plane. The second one was 0, 1, fy. And then finally recall that because these were both vectors that lay in that plane, their cross product could be used to find the area of that plane. Now, of course, I don't really know how long either of these are because they're solely functions of whatever these partial derivatives are. So I also don't know that their cross product is going to give me the area I'm after. So I'm going to multiply these by a factor. I'll multiply this one by delta x, whose size I can control, so I can make it as large or small as I want. I can even make it infinitesimally small, and I'll multiply this one by delta y. Well, now let's go about taking their cross product. And of course, we've already done that because that was how we found the direction numbers for this particular plane. The cross product of these produces a new vector, which is fx, fy, and -1. And of course, it's still times delta x, delta y. Those didn't participate in the cross product because they're just scalar multiples. So now they're scalar multiples that are part of the result of the cross product. Well, if this cross product, in essence, gave me the area of that little piece, then all I need to do is find its size, and that will give me the magnitude of the area. So what I'll need to do is find the size or the magnitude of this vector. And of course, if I do that, and then I let delta x and delta y become as small as I want them to be, all I'm going to have to do is integrate, choosing appropriate limits to cover this entire surface, and these infinitesimal pieces of parallelogram will have exactly the same size as each small piece of surface. And the integral will paper the entire surface, and I'll get the surface area. Of course, the size of this is going to be the square root of the sum of their squares. It's not exactly a friendly function. But this is in essence what it'll look like. I'll have an integral over x and an integral over y. The interior function will be the size of this particular vector. That will be the square root of fx squared plus fy squared plus 1. And then I'll integrate that dy dx. And this will do it. That is, this will find the area of these infinitesimally small parallelograms, each one tangent to the surface. And if I choose appropriate limits of integration, I'll actually paper the entire surface with it. So this looks surprisingly like the integrals we've done in order to find volume, except then we were integrating the height of the function as a function of its base. Here, we're actually choosing a contrived function, which is not necessarily the altitude. It's not the z value. Instead, I'll have to express whatever the function of this is as a function of z. It's going to be z equals some function of x and y. the partials of that function with respect to x and y, inserted into this square root function, will then give me the area of the parallelograms, which when sufficiently added together with appropriate choice of limits, and again, these limits are going to be just like they were for any of these other functions. The basis could be functionally defined. This could be done in spherical coordinates or rectangular coordinates, but if I can perform this integral, I will get the surface area of this function.